This video is about the impedance of capacitors. It corresponds to section 10.2.2 of Applied Analog Electronics. Now, we can go back to the definition of impedance to take a look at how we can compute the impedance of a capacitor. Remember that impedance is just voltage over current, and we're interested in the voltage and current for a fixed capacitor C. We can go back to what we know about capacitors, things like Q equals C times V. The charge is the capacitance times the voltage. And the current is the derivative of the charge with respect to time. So by the multiplication rule, we just had that that's C dV dt plus V dC dt. And we can make an important simplification here. We were saying we were interested in what does this do for a constant capacitor. Well, if the capacitor is constant, it doesn't change with time. dC dt is 0, and this term goes away. Okay, so we have this differential equation which says how our capacitor behaves. What are we interested in? We're interested in what happens when we put a sinusoid as the applied voltage. So let's say V equals some amplitude times e to the j omega t plus phi. This is our canonical generic sinusoid. There's an angular frequency omega, some phase offset at time 0 of phi, there's an amplitude of a. Everything there is cool. What is the derivative of this? And more particularly, what's the current? C times the derivative of this. Well, exponentials are one of the nicest things in the world to take derivatives of. We're just going to get j omega e to the j omega t plus phi. So now if we take v over I, lots of things cancel here. We're going to get 1 over j omega c because the amplitudes cancel and the sinusoidal terms cancel. Right? This is the impedance of a capacitor. And notice that it's not changing with time, so it's a constant in the sense that it doesn't change with time, but it does depend on what angular frequency we were doing here. And that's an important point here, that capacitors change their impedance with the frequency of the sinusoid you put into them. Let's look at sort of extreme cases. What happens if omega is 0 radians per second? So 0 hertz, if we think of it in terms of frequency instead of angular frequency. Remember, we can do omega equals 2 pi f to convert between frequency and angular frequency. So if frequency is 0 hertz, omega is going to be 0 radians per second. What is that? That's DC. Nothing's changing. What do we expect to have happen? Well, remember there's two plates separated by an insulator. We can't put any electrons through that insulator, so we expect no current. All right. What happens if we plug into this formula? If we plug 0 into this formula, we get Z sub C at 0 hertz is infinite. We get no current, have a voltage across there. It's exactly what we expect. Capacitors are used for blocking DC. What happens if omega goes off to infinity? Looking now at very high frequencies. Well, 1 over j omega c goes to 0. And I suppose I should write that as 0 ohms, because the units of impedance being a voltage divided by a current is ohms. So that says that at very high frequencies this thing acts like a short circuit. Capacitors are short circuits at very high frequencies, open circuits at very low frequencies. In fact, we can do something where we plot the impedance versus the frequency, and we'll do this on a log-log plot. And what we're going to get is something that slopes down like this, where this slope is -1 decade per decade. That is to say, the impedance is inversely related to the frequency. Okay, what else can we do with capacitance? Well, we want to know what happens if we put two of them in parallel, put two of them in series. For that matter, what happens if we put a capacitor and a resistor in series? Let's look at some of those things mathematically. All right, let's start with capacitors in parallel. Okay, what do we have? If we've got two capacitors in parallel, let's say C1 and C2. Well, we had a formula for the impedance of capacitors in parallel. In fact, while we're at it, let's do three capacitors, just generalizing. We can do any number. What is the formula for impedances in parallel? Well, that was 1 over Z1 plus 1 over Z2 plus 1 over Z3. Well, what are Z1, Z2, and Z3? Well, that's the impedance of each of these capacitors. So Z1 is 1 over J omega C1. Z2 is 1 over J omega C2, and so on. All right, we can take these formulas and stick them in there and get that Z equals 1 over J omega C1 plus J omega C2 plus J omega C3. But this thing on the bottom, that can be factored. And we can write this as Z equals 1 over J omega C1 plus C2 plus C3. And that's the formula for the impedance of a capacitor. Capacitor, that is C1 plus C2 plus C3 as its capacitance. So this three capacitors in parallel behaves exactly like a single capacitor that has the capacitance, the sum of these individual capacitors. So capacitors in parallel add. Now this is different from what resistors did. Resistors in series added. Capacitors in parallel add. And that's because the impedances behave the way they do. The currents add up. Everything is working out just the way we want because capacitance is coming out on the bottom. It's inversely related to the impedance. All right, what happens for capacitors in series? We'll do the same basic analysis here. Let's again take three capacitors, C1, C2, C3, and now we know these are in series, so their impedances add. Z equals Z1 plus Z2 plus Z3, which is 1 over J omega C1 plus 1 over J omega C2 plus 1 over J omega C3. And again, we've got that 1 over J omega in all those terms, so we can take that front here, 1 over J omega times 1 over C1 plus 1 over C1 plus 1 over C2 plus 1 over C3. All right, that's not quite in the form of a capacitor. But if we rewrite it just a little bit as 1 over J omega times 1 over C1 plus 1 over C2 plus 1 over C3, now it looks just like the formula for a capacitor, the impedance of a capacitor, and the capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Capacitors in series follow the same formula that resistors in parallel did. And you add their inverses and invert that. So we don't really have new formulas here. We just have to know that capacitances are the inverse of the impedance. They're inversely there, so we end up swapping the parallel and series formula from what we had for impedances. Okay, so let's look at what happens if we have a capacitor and a resistor in series. What's that going to do? Well, you can think about this very simply in terms of what happens at 0 frequency and what happens at infinite frequency. Remember, at 0 frequency, the capacitor behaves like an open circuit. So this thing is basically just going to block DC. And in fact, at very low frequencies, this is going to have a huge impedance. The impedance of this thing is going to be 1 over j omega c plus r. So when omega is really tiny, this term out here is going to dominate. The plus r is not going to change things much, and it's going to look just like a capacitor. At high frequency, well, the 1 over j omega c is going to disappear, get very, very tiny, and it's going to look just like a resistor. So we expect something that'll be like a capacitor at low frequency and like a resistor at high frequency, where this line looks like just R, and this line looks like 1 over omega c. And here I'm looking at the magnitude of the impedance. And in fact, what I did is I measured an actual electrolytic capacitor, and let's see what we got. All right, so this was nominally a 10 microfarad electrolytic capacitor. And the green line there is what we would expect if it was a 10 microfarad capacitor and nothing else. And the kind of purplish line, maybe I should turn my head off here so that you can see the whole plot. The purplish line is the actual measurements I made. Lots and lots of data points using the Analog Discovery 2. And the blue line is a model where I fitted a capacitor plus a resistor to this measurement of an electrolytic capacitor. And what you can see is at low frequencies, it looks an awful lot like, well, not a 10 microfarad, but an 8.67 microfarad capacitor. And at high frequencies, it's pretty flat, not exactly, but it looks like about 2.5 ohms. And so we end up with this thing that at low frequencies it looks like a capacitor, at high frequencies it looks pretty much like a resistor. And there's sort of a corner frequency where it switches between those two. We'll look at corner frequencies and stuff more later on. But for an electrolytic capacitor, if I wanted to use this thing at frequencies above 7 kilohertz, it's not acting like a capacitor anymore. And so you have to be careful about series resistances in your capacitors. Now, we're going to be using we won't be using electrolytic capacitors, we'll be using ceramic capacitors. And the ceramic capacitors have a much smaller series resistance, and so the frequencies we'll be dealing with, we can treat them just like capacitors. But this is one of the reasons why we don't use electrolytics much in this course, is because they don't really work like capacitors at high frequencies. All right. So what else do we need to know about capacitors? Now, there's one thing that may be bothering you a little bit, and that is the impedance of the capacitor is purely imaginary. It's 1 over j omega c. And if you multiply top and bottom by j, it's minus j over omega c. So it's a negative imaginary number. What does that mean? Well, you can think about it in that the current and the voltage aren't in phase with each other. The voltage and the current don't go up and down at the same time. They're doing it at the same frequency, but not at the same time. So let's take a quick look at the plot of what I mean by that. Okay, the purplish line here is a voltage. The blue line is a current. And if you were putting voltage across a capacitor, and here I've did what would be appropriate for 0.22 microfarad capacitor, you'd see that the current is at its maximum when the voltage is rising fastest, and the current is at a minimum when the voltage is dropping fastest. So this puts them not happening. The biggest current isn't when the voltage is biggest, it's when the voltage is changing the fastest. And the smallest current isn't when the voltage is the smallest, it's when the voltage is dropping the fastest. You see this from the blue vertical line there, which is where the peak current is, and the purple vertical line, which is where the peak voltage is. And the difference between these two things is a 90-degree phase shift. And that's rotating from the real axis, where resistors are and where there's phase change of 0, rotating downward 90 degrees puts you on the negative imaginary axis. So the phase change is sort of what direction you are from the origin on the complex plane. If you're on the positive real axis, you've got a phase change of 0. If you're on the negative imaginary axis, you've got a phase change of minus 90 degrees. That is to say that the voltage is 90 degrees behind the current. Okay, we'll look more at phase shift a little bit in this class, but for the most part, we're going to be interested in the magnitude of impedance and not so much in the phase. So if the phase shift is bothering you a little bit at the moment, don't worry about it too much, but do try and understand what happens to the magnitude of the impedance. And do always keep all your calculations in the full complex numbers, because when you add and subtract things, the phase matters then. Okay, that's probably enough for now on the impedance of capacitors.